Hello.
Um, Good evening.
Alright, so tonight is going to be our last experiment. Experiment 12 is calorimetry and specific heat. So if you can turn on page 100 or 99, I got 100 in my packet.
Okay.
So turn on to page 99 or 100.
Yeah.
Straight into the lab report sheet.
Okay.
And I'll explain shortly the experiment, and then we'll perform one trial. So once again, just turn on the lab manual on page 99 or 100. Okay, either one of these copies that will show this sheet. That's your report sheet. We have a chance to do one trial. There are two trials to be done, but then I only have a chance to do one trial. I'll show how to do one trial.
Oh yeah.
Right?
Yeah. So it looks like we just only need to deal with one trial in the calorimetry sheet?
So far we have one trial possibility for tonight. Because for the second trial might take a little bit more beyond the time dedicated. So we'll do one trial. All right, are we together? So let me share with you the PowerPoint. So we'll go over the steps that are to be done. So the whole idea basically is to be able to measure the specific heat of an unknown metal. So we have an unknown metal, okay, some metal with an unknown identity. So trying to figure out the specific heat of that unknown metal. Now, specific heat, by definition, is the temperature, the amount of heat required to raise the temperature of 1 gram material by 1 degree Celsius. So if you carve out, let's say 1 gram, so your unknown metal, and then let's say here's the metal. Okay, so here's the metal unknown. Now you can see them. So assuming here's the metal unknown. So I'm going to scoop out 1 gram of that unknown metal. And then I want to keep delivering heat to it, keep raising its temperature until that temperature becomes 1 degree. Whatever that room temperature, keep adding heat up until that metal, that 1 gram of that metal, unknown, raised up by 1 degree. How much heat it took up to raise its temperature from the initial temperature to final temperature by 1 degree is called specific heat. So it's a little bit more unique definition. Okay, the question is, how do you approach the measurements? So the measurements to be approached using what's known as the calorimeter setup. So using this typical setup for all these thermochemical reactions, including figuring out the specific heat of an unknown metal. So I want to use that setup that has the following. So it has a thick-walled insulator. So this is styrofoam insulator. Other materials are possible, but then this is a good insulator. Just made out of styrofoam. The cover basically is just not mentioned styrofoam, but then just a cover, plastic cover that has a mountain thermometer. So I'm using a thermometer and a place to plug in that thermometer, and then the walls of that insulator. This time around styrofoam. The setup is primitive as far as the setup. However, the setup is good enough to give us a good amount of information to identify the unknown. Okay, so I'll give you some aspects of the unknowns and some possible unknowns. So you guys, at the end of the experiment, you figure out the specific heat of that unknown and try to identify the unknown. So let's see how this is to be done. All right, so the setup is as following. So I'm going to measure a specific amount of that metal. It doesn't matter how much. Should I measure 1 gram, 10 gram, kilogram? It doesn't matter the initial amount. Specific heat is intrinsic property. It concerns with the building of that material. Intrinsic to means careless about the amount or the volume of that material. It just concerns with the building, the interconnections, the atomic, the molecular picture of how those building blocks of that material is made out of. So the property shows either one. If you measure 1 gram, 10 grams, a kilogram, it doesn't matter the amount that you scooped and measured. Okay? It's going to reveal itself regardless of the initial amount. So it doesn't matter the initial amount. I'm going to just challenge maybe 50 grams or so of that metal. I'm going to heat up that metal initially to a specific temperature. So I'm choosing to heat up the metal inside hot water, hot boiling water. So that means the initial temperature of that metal has to achieve the same as the hot water, but I need to measure it. I need to verify it. It's not typically 100. The typical boiling temperature of that water is 100. If you snug in that metal inside that boiling water, don't assume to be 100. It has to be measured. So we're going to measure that initial temperature of that hot metal. And then on the side, we'll want to prepare the calorimeter. So this is the calorimeter that is made out of styrofoam. And then we want to prepare a thermometer to collect data. So once you're ready as far as to transfer that metal, so you uncover the lid, scoop that metal from that tube, and then eventually deliver it straight into that calorimeter. And then wait until that process finalizes itself, and explain to you shortly what does it mean. So the process will finalize itself into some number, some temperature. So let me ask you this. Let's say if you're trying to do something, trying to do some measurements, let's say if you want to measure temperature of a material, let's say pick and choose something. Okay, so here's a beaker. Okay, so what's the initial temperature of that beaker if I want to measure the temperature change? So I guess you touch it with thermometer and try to measure the initial temperature. Okay, so we're definitely clear about that concept. Let's say I want to heat up that beaker. And what must have been the final temperature upon heating an object? What do you think? I don't know. Well, it depends on how much heat you delivered. So the final temperature is whenever you decide to stop making the measurements, correct? So here's my thermometer. Okay. So here's my thermometer. Look. So this is an object. Stick around with me. Okay. So here's the object. An object. It's not a thermochemical process object. So the initial temperature, here's my thermometer. Just check the initial temperature. That's that. Now I want to heat that object, so continue adding heat until that object is gone hot, and then here's the thermometer once again, and then you stop the measurements, correct? So you only took 2 measurements, the initial and final. So the final temperature, whenever you decide to measure that beaker at any point of heating, correct? Let's say if you want to heat it a little bit less, so whatever that temperature of that final heating, that would give you the final temperature. The final temperature is based on what you thought the final measurements of taking the temperature. True? This time around, the final temperature of thermochemical process is not the same, which is a little bit confusing. So let me explain to you why. The final temperature of the process has to be measured at the beginning of the process, before you start the process even. For example, let's say, my analogy, let's say you walked into a room with a hot drink. So when you walked into that room, I say stop right there at the door, measure the initial temperature. I gave you a thermometer, so you'll be able to measure the initial temperature of that hot drink. While there, you saw at the door, I'm asking you to measure the final temperature as if you walked in and you stayed in the room for half an hour. But you're still at the door. So at the time of measuring the initial temperature of that hot drink, I'm asking you, can you measure the final temperature of the hot drink? But you'd say it doesn't make sense. I mean, you can measure the initial temperature. So here's my hot drink one more time. So hot drink as you walked in. This is just an analogy. What's the initial temperature? Well, just plug in the thermometer, measure it. What's the final temperature? Well, final temperature is, well, what does it want to do with that hot drink? Once I let you in the room, definitely the hot drinks will cool down, get cooler. So eventually the final temperature is whatever that you decide to measure that final temperature. That's what you thought, which is wrong. So for any thermochemical process, the final temperature has to be measured at the same time or measuring the initial temperature. At the same time. The initial and final temperature needs to be measured at the same time. Both needs to be measured at the same time. And it doesn't make sense. Yeah, very difficult. How do you measure these? So as you walked into that room, before you walking in, I'm asking you to measure the initial and final temperature of that hot drink. It's incredible. Okay? So it's not doable. So the reason why we're going to do that final measurement, the final temperature, by what's known as extrapolation. Okay? I'll show you in a second how to do it using software. So tonight we're going to be using software to measure the final temperature by the process of extrapolation. So to begin, let's go back. So we all turn to page 99 or 100. So we're going to measure first a small amount of water. So we're going to add a small amount of water inside that cup and measure a specific amount of that metal. Then heat up that metal, then transfer it into that water, into that cup, into that styrofoam cup, and then figure out the initial final temperature at the beginning of the process. At the beginning of the process. All right, so hopefully they can digest what was it about to be done. So now, so this is what I'm trying to say. Okay, so eventually you're going to see on the board a plot, a graph between time on the x-axis and on the y-axis temperatures. So at the beginning of the plot, so whatever that straight line showing with time passes, the same temperature, it means this is typically the room temperature before any process kicks in. Once you add a metal, the water inside the calorimeter is going to heat up a little bit, so temperatures will rise up. Continue on rising until some point, eventually it's going to slow down. It's going to jump, it's going to rise, eventually it's going to plateau a little bit, then it's going to slow down back to the room temperature. Okay, so we're going to see the following plot that has three portions. The first portion represents the room temperature. The jump indicates the amount of heat delivered to the water by the heated metal. That plateauing, it means the temperature cannot rise anymore. It'll plateau for a second, maybe for a while, and then eventually it's going to start dropping because that wall of that container is not 100% insulated. Okay, eventually whatever that hot material is going to cool down eventually. Okay, so it's going to somehow go down and decrease in temperature after a while, back to room temperature. Okay, that's always the tendency of these containers with the stuff inside. And that feature is going to be shown later on. So I'm going to track that feature of reducing or decreasing temperature. I want to extrapolate using the plot back to the initial time mixing, which is at the initial time mixing, assuming here's the kink between the initial temperature and some activities occurred. At the initial time of mixing, the intercept of that vertical line with the line drawn from that straight line of the later on section of that curve is going to give me the final temperature. So that intercept point is my final temperature. So let me explain to you how to do it. All right, so back to the measurement. So first, I want to measure any amount of metal. Okay, so I guess any amount, let's decide on 50 grams. So just follow measurements. Can you see that screen? Okay, so I'm going to zero that screen. So I'm measuring roughly 50 grams of metal. one more piece. Okay, that's good enough. Alright, so that's good enough. So record that number. So what we have? Can you see those numbers? What's the mass of the metal?
Appears to be 49.41 grams.
Right, so record that number. The next step, I want to measure the mass of water. So I want to snug in a small amount of water in here. So I guess let me measure 50. Okay, comfortable. What you want basically is to have enough of water initially inside that calorimeter in such a way as to cover the size of that metal. So if this is the beaker, so notice, so what's the size predicted based on that amount of metal? 20, 25 milliliter? Agree? Can see it? Because this is about 50 milliliter beaker. So this is a 50 milliliter beaker. And this is the amount of that metal inside that beaker. So I guess somewhere around maybe 20 is 20. So still, I need to make sure that whatever that water inside that cup should be at least above and beyond that volume. So I want to measure, let's say, 50 milliliter. So 50 milliliter of DI water, somewhere around 50 grams, agree? So let's tear that calorimeter and deliver 50 grams, meaning add in 50 milliliter. I can add a little bit more. So since I measured 50 grams, almost 50 grams of metal, let me make this one around 75 milliliter, just to make sure. Okay, good enough. All right, so that's the initial mass of water. So record that number. So the initial mass of water, can you see that value? Can you read that value for me?
74.54.
Very good. So that's the mass of water in the calorimeter in grams. The next step is I want to heat up the metal. So let me show the setup. So on the side, I was heating water. So I have a container, a beaker, size-old beaker, 600 milliliter. I added some water, so now it's already boiling. So I want to insert the metal inside that large test tube, and then I want to leave it or submerge it inside that hot water for at least 10 minutes because it would not heat up right away. It's going to take a while. So I'm going to keep heating until at least achieve a good number, very close to that heating water, which is boiling water, which is 100 degrees. It may not be 100 degrees, but I need to measure it. Okay. So first, carefully transfer that metal that we measured into that dry test tube. Okay. So here's the transfer process. Snug it in. So I'm going to submerge it inside the hot water and keep it suspended. So notice the hot water completely, so notice the hot water completely covers, so above, so the hot water, you can see it? So here's the level of that metal, and the hot water should be above that level of that metal, just to make sure all the metal is heating up. Just to make sure everything is working and hot metal receives at the specific temperature without prediction. I don't want to predict the hot metal is the same as the boiling temperature, 100, but I want to measure it. So here's my thermometer. So I want to add in that thermometer on top of that test tube. So I'm snugging that thermometer on top of that test tube to be able to measure what sort of environment inside that test tube. Okay. So a way to read the temperatures. So I have the thermometer. So the thermometer is plugged into the screen. So here's the thermometer screen. So 31. See it? So that's the thermometer, the temperature inside the metal. So inside the metal, the temperature is still cold. Now it's rising up. So let me just put that in the background to be able to see both. See that? Can you see that temperature? Now that temperature, which is the temperature of that metal inside that test tube. Alright, so on the side, I prepared the following calorimeter. So this calorimeter has in it so far the measured 74.54 grams of the eye water. And I've plugged in the thermometer. So here's another thermometer. And I'm ready to, while I'm waiting for that melt to heat up, I'm going to keep monitoring that temperature until that temperature of the metal would say somewhere around close to 100. Will take a while. I guess the hotter the better. Okay, so any temperature above 50 will do. It doesn't matter. It doesn't have to be exactly 100 or close to 100. But the hotter the better as far as the results. Alright, so far the temperature is still under 40. So it's going to take a while. The temperature. So the temperature. So the temperature of that hot metal is achieved or transferred from the air above it. So what surrounds that tube is water, boiling water. What's inside that tube? Just air, the metal and the air. Eventually, so by convection is what gets the air above that metal to be heating, and conduction basically because the water is boiling and touches the surface of that test tube. Eventually, by conduction, it's going to conduct the temperatures. But since these metals are tiny spheres or tiny assemblage of the metal beads, they're not connected. So conduction would not work. So a portion of it basically based on the contact. If there's a contact, so heat will go from place to place by conduction based on the contact. If there's hardly contact, it waits for the air in between them. Because he's one molecule, he's another one, or he's a cluster of metal, he's another cluster, maybe touch it by one point. You need a complete contact, so transfer heat from one to another by conduction. If there's separation and air in between, how he's going to go from place to place? Convection. It's going to hop into the air onto the other portion of that metal. So it's going to take a while. So there's a combination of conduction and convection. Eventually, it's going to allow the temperature of the metal to rise up. I'll give it a chance for 10 minutes. So let's time ourselves. So right now, 7:25. So let's give it a chance for 10 minutes. Let's see whatever that temperature is going to be at. We're going to transfer it, whatever after 10 minutes. Okay? Because there is no way for that temperature to achieve the same as the boiling temperature. And I'm presumed to have 100 point temperature to that boiling temperature, to that boiling water. All right. Now for the calorimeter setup, so here's the preparation part of it. So I'm preparing a software that software has the following features. So I'm going to go to that clock and just let it go continuous, either by set time, so you can collect data based on set time, or by continuously collecting data. So I'm going to set it to continuously collect data, and then I'm going to just wait until I'm ready for that temperature of that metal to achieve the highest. Okay. And so far the temperatures temperatures at around 53 and increasing. That's a good part. Alright, so we're going to wait until 7:35. Alright, so back to that page 99 or page 190, depending. Alright, so let's write down a few facts. So the temperature of the hot metal, we're going to leave it alone until we're satisfied with the hottest temperature on that screen of the metal. So we're going to just leave it alone. But we can write down the initial temperature of the water inside the calorimeter. Alright, so line number 3, third line, that would say the third line, that would say the hot temperature of the metal. The initial temperature of the metal is the hot temperature of the metal, because I'm trying to heat it. So the third line is, leave it blank for a second. I can answer the fourth line, the temperature, the initial temperature of the water inside the calorimeter. Okay. And what's that temperature? Can you tell me what's the initial temperature of the water inside the calorimeter? Because I measured almost 75 grams of water inside the calorimeter. And what's that temperature? What's that initial temperature? That water inside the calorimeter?
Celsius.
21.3, right? Let's write down that number. Alright, so how is the temperature going on this side? So it's still in the 50s. So I have another thermometer. So this one is a little bit limited because it has that little bit fatty end. And it does not allow it to go nicely inside the test tube. I can use another thermometer. So this is a little bit more, like a little bit more robust way. So what I've done basically, I just removed the first thermometer, because that initial thermometer that is supposed to measure the temperature of the metal has a little bit more wider, like short tip and wider body at the end where the electronic is. So I removed it and I substitute that temperature with another thermometer. So that thermometer has that look. It's a little bit more slick, a little bit more thin. I'm able to go as deep as the metal themselves. So I'll be able to measure at the metal itself. Okay. So I'll be able to measure the temperatures right at the metal. All right, not bad. Now the temperatures are reading 79 and climbing. You see those temperatures? Okay, not bad. So it is increasing rapidly. But let's see what's the hottest. So I still have another 3 minutes. But 84 is pretty good.
Where is the temperature?
So this is measuring. So this screen right here. So this screen right here is measuring that 85.3 so far is measuring the temperature of the metal. So I'm measuring the temperature of the metal, and here's the thermometer. So here's the thermometer measuring that temperature. Okay, and here's the value. So this measures the temperature of the metal inside the hot water. The second thermometer, got two thermometers. The second thermometer, which is this one, is knocked into the inside the calorimeter and measures the temperature of the water. Because I measured almost 75 grams of water inside that calorimeter. So the second thermometer is measuring temperature of that water inside the calorimeter. Okay. All right, so far so good. So temperature so far is almost 89. So let's give it a chance until I see a number that does not change, and within a minute, then I'll accept it. So far it is changing. So this is almost my 9 minutes, entering the 10th minute. But the temperature keeps on rising, so I want to see that temperature not move in, or mean to be with the same value for at least a minute. Then I'll scoop it out and dump it inside that water, inside the calorimeter. I guess there's a cooling time. So I got 9, but then I guess cool down a little bit. even the temperature inside the calorimeter warmed up a bit. Temperature went up from 21.3 to 21.6. So he's 90. So let's monitor on that 90. If there's no way and chance to deliver hotter temperature at 90, I'm going to just stick around to 90. So let's monitor that at 90.2. Let's see how stable it's going to be. Okay, so it's not moving. So now it's flickering to 90.3, between 9.2 and 9.3. But within a minute, if that value does not go up drastically or go down drastically, we're going to just accept it. It looks like it's not moving. Agree? So right now it is at 90.3, but it's not moving. So I guess if we sort of stuck at around 90.3, it's gonna take a while to jump to 90.4. I'm presuming. So I guess we can stop the heat of that metal, and then I'm gonna transfer the metal straight into that calorimeter and follow the software. But before, let me initiate the software. So once again, check it on that timer, continuous, pretty good. And I'm gonna start the software. So easy collect. So now the software is starting. Yeah, remains to be solid at 90.3. So let's record the initial temperature of the metal as 90.3. So the third line, temperature of the hot metal, so that is the initial temperature of the metal. It is at 90.3. Agree? It's not changing. Alright, so we're just about ready to transfer the metal. So just about ready to transfer the metal. So I want to position the two together.
So it's the 90.3, that's the temperature of the hot metal?
That is the temperature of the hot metal. That's the initial temperature of the hot metal.
Okay.
And then I'm ready to transfer it straight into the cold water inside the calorimeter. Okay. So I want to bring the two to be so close as possible. So I'm going to remove that thermometer. So it's no longer measuring. And now I want to... So the technique is by taking the least amount of time. So that transfer has to be done with the least amount of time. So I'm going to keep it and keep that metal inside the water. I remove all the obstacles while the software is running. So I'm going to just shove that cover. I'm going to remove that cover for a second, and the metal quickly recover. So you're going to end up having some sort of a zigzag on that screen. So that's the result of just shoveling the two and add in the hot metal. Okay, so it's still measuring the temperature in the water. So I open the calorimeter. Okay, the thermometer still measures the temperature of the water. So use the metal. just so give them enough of shaking so all the metal now surrounded with water. So we just keep it for a while. And shut off that water. So now I'm done with that water. So as far as the calorimeter, so I'm trying to tape it in such a way as the cover remains to be a snug fit and remains to be tight. So that's the calorimeter. All right. Let's see what we've done. All right. So now I'll be waiting for the results. It's gonna take a while. So what's I'm waiting for? So in that now software, so I'm looking at a graph of time versus temperature. Time is on the x-axis, temperature is on y-axis. So let me just let me reassign that value. So I've just done some enhancement, just cosmetic. All right, and then I'm going to squeeze and see exactly what's going on this end. All right, so at the beginning, so this is what happened. So at the beginning, so as I removed the cover of that calorimeter, eventually I allowed that hot metal. I guess some beads somehow just cluster in one little area, and the thermometer sends extremely hot temperature. But eventually, the rest of them, as you cover them with water, eventually they're gonna give us like a more robust, more sort of an overall temperature of all of them to be collected, not just the ones that are suddenly touching the, because when I transfer it, the whole area is very tiny, and you transfer some beads, and eventually some metal is going to touch that thermometer sensor, the metallic portion of it is going to somehow spike. But then, so don't worry about that initial spike, just an artificial based on that beads are touching the sensor straight. But the rest of them are the overall behavior of all of them inside the water. Okay, so I'm going to rely on the rest of them behavior, that line. What I'm waiting for until I satisfy with the collection of data. So I'm waiting for that line to slightly go with a slight negative sloping. Okay, so mounted those temperatures right now at around 26.2. So I'm waiting for that temperature to dip a little bit, to go down to 26, maybe 0.1 or 26. Let's see how it's gonna occur. So I'm waiting for that temperature to dip a little bit. Right now, it is at around 26.2. So it's going to take a while. So I'm going to give it a chance of 10 minutes or so, 15 minutes to cool down a little bit. So right now it's not giving me any sense that it's going to go down. But let's see if it's going to go down a little bit. All right, so I'm waiting for that 26.2 to say 26.3. So it's 26.1, then 20.0, something like this. All I want basically is to have that feature which is sloping in negative direction by slight sloping. So slight sloping, that would give me enough of handle to analyze data correctly. Because I want that line. Okay, let me just show you exactly what is it I'm waiting for. So what must have occurred? That's what I'm waiting for. So I'm waiting for, so here's the feature of that plot. It's going to jump after dumping the metal. Eventually it's going to somehow slope in a negative direction because eventually he's going to get lost. So here's the calorimeter. Eventually leak and he's going to deliver, is going to turn that temperature from hot to cold slowly. So now it's flickering between 26.2 to 26.1. It's going to continue on going down. Eventually it's going to go down, decrease until the room temperature, whatever that room temperature. Agree? Because that container is not perfect insulated. Okay, so that feature is going to help analyze the final temperature. The final temperature, we already missed it. So here's the misperception. So for any process except thermochemical process, the initial temperature is initial temperature. These are in common, but then the final temperature, especially for the thermochemical process, only true if that to be measured at the beginning of the process. Where's the beginning of the process? Right there. So what that action that took place, that's the beginning of the process. At that beginning of the process, the initial temperature is whatever that initial temperature, somewhere around, what is that, 21.8 something, okay? But the final temperature is not whatever that final temperature shown on the graph, on the plot. It's not. Final temperature should be measured at the beginning of the process, should be measured there. At the beginning of the process, which is impossible. So we always measure the final temperature at the same time we measure the initial temperature. So this is our technique, especially for the thermochemical process. So thermochemistry requires just primitive tools, thermometer and calorimeter, and sometimes timer or electronics, as I'm showing. But with these primitive tools, be able to measure lots of things: specific heat of metals, specific heat of solutions, heat of vaporization, for example, enthalpy of dissolving salt in water, enthalpy of reactions. So be able to measure a tremendous amount of measurements and informations. And they're all scientific, they're all true, as simple as utilizing and using thermometer and calorimeter, which is styrofoam, cheap material, plus maybe a timer or maybe a software. So that combination will give you access to be able to measure many materials, many aspects of scientific constants. So I'll wait a little bit more until that value becomes 26.0. Then I'll go ahead and measure the specific heat. All right, so that feature is very important for me as far as the slight negative sloping. Once I come up with that a sense of negative sloping, I'm going to create a straight line. So I'm going to select a portion of it and create a straight line based on that negative sloping. I'm going to go back to the initial time mixing. I'm going to create a vertical line. So here's the initial time mixing, assuming. So here's the final temperature, which is we already missed. The final temperature is higher than the hottest temperature shown on the plot. Definitely, this is an exception. So that little spike in here is just artificial. I guess few beats comes in and contact it. So if this is the thermometer, and that's the sensor portion of that thermometer, a few beats of at around 90 degrees straight contact that sensors, the sensor is going to jack up its temperature, still surrounded inside the water, but then that temperature that will give us hotter values, which is not acceptable. So these are artificial jump. It's not part of that curve. So most likely the curve is going to bend at around this area. But no matter what's the temperature shown on that plot, the final temperature is always higher. If this is an exothermic reaction, meaning the temperature after you mix it to is hotter, we call that feature exothermic reaction because temperature increased. the final temperature is always higher than the highest temperature shown on the plot. So the final temperature is not there, it's not there, it's not there. It's not when you decide to stop measuring. Any other processes, let's say if you travel in and someone said, okay, so what's your initial speed from the idle car not moving? You would say, okay, 0, but then, okay, go ahead and just move your car and tell me the speedometer. Okay, so whatever that measurement, it's called the final measurement, whatever that you decide to measure it. So it is at 12. The final temperature for the thermochemical process is not when you decide to stop the measurement. So that's why I kept saying it is already decided for you, and it's already occurred at the beginning of the process, and you already missed it. It should be measured at the beginning of the process, which is impossible. How do you measure it? And the process did not kick in. You haven't started yet the process, but you need to measure the final temperature of that process that haven't started yet. It's kind of awkward, yeah? That would make it impossible to measure. The reason why we have to measure it using software or plotting. All right, so where are we going with this? So I'm waiting until that temperature goes down to 26.0. It's going to take a while. So not so bad for that cheap container. So this is just a few bucks, and got that container with the least amount of expenses. But look at the robust temperature inside of it. Yeah, it just went down from 26.2 to 26.1, and it took a while to get to that temperature, I guess. But I'd rather see it going down a little bit further. All right, so let's put a few things together. All right, so by the time the temperature goes down a little bit more, so let me just move the setup. Okay, so on the side, let's analyze what we have. Okay. So the theory goes this way. The amount of heat. So I'm going to represent the heat with that letter Q. So that's the heat exchanged by the metal. So here's my thermometer. Let me just bring another setup. So assuming here's another setup. Here's the cup. Inside of it is water, and I dipped in metal, heated metal. Now, the water and the metal together exchanged heat. All together, upon the exchange, at the end of the day, so let's say if the metal delivered heat, because it's going to cool down, it's going to deliver heat to who? To the water inside that calorimeter. Water took up that heat coming from that metal, and it's going to heat up a little bit. It's going to increase its temperature. The metal, however, its temperature decreased from the initial hot temperature to a lower temperature. Both are going to wind up having the same final temperature. But the initial temperature of the water, the cold water, is cold. The final temperature is the final temperature of that process. The initial temperature of the metal added is hot. It's going to wind up having the same final temperature of together the water and the metal. So the same as, let's say, me and you in one room, let's say, by analogy, and I took out $5 out of my pocket and I give it to you. So I've lent you $5. Okay, so as far as your point of view, you gain 5. My point of view, I lost 5. At the end of the day, together, while being inside the room, $5 out of my pocket into your bucket. At the end of the day, well, what's the amount of total change of the amount of money inside the room? Nothing. There's 5 out of my bucket into your bucket, but eventually if I have 5 and you got none, eventually the 5 get out of my bucket, land it into your bucket. At the end of the day, there's no difference in the total amount of money in the room. That's what I'm trying to say. So I'm gonna equate to, or if I add the amount of heat exchange, the heat came out from the metal, Q sub M, plus the heat exchange by the water, so I'm going to symbolize that as QW. All that heat exchange, based on my analogy, will add up to 0. Agree? All right. So now let's solve for that Q sub n for the metal. So Q sub metal, the amount of heat for the metal equals. So moving over QW for the water to the other side. So that belongs to the water. QW. So it takes on a negative value minus Q for the water. Okay. So substitute based on what we know. Okay. Every Q term, every heat term has three simple terms: mass, specific heat, and delta T. So memorize this on the side. So every Q, which is heat, this is heat. Every Q, every term that represents heat, has in it three terms: mass, specific heat, and delta T. It has always three terms. So that means Q for the metal should have in it the mass of the metal, specific heat of the metal, delta T for the metal. Okay, so let's write them down. So I'm going to write down all the terms, or the three terms that belong to the metal, which is the mass of the metal. What's the mass of the metal? What was it? I measured 49.41.
49.41.
Right? So 49.41 grams. Multiply this by the specific heat of the metal. Well, it is unknown this time, so I'm going to leave it as unknown. So this is the specific heat of the metal. So this is the metal. Multiply this by the delta T for the metal. What was the initial temperature of the metal? Because I want to figure out delta T for the metal. Delta T is always T final minus T initial. What was the T initial? What was
50.2.
So, what was it? 21.3 or 2, you said, right?
That's water.
The initial temperature, I'm sorry. So the initial temperature of the metal, it's a hot metal, so therefore, what was the temperature? 90.3. So the initial temperature of the water, because the water was heated inside the boiling water. And remember that number, 90.3 Celsius. So that was the initial temperature for the metal. The final temperature is coming up. So that I don't know. Okay, so we're gonna wait. So I'm gonna write down the following. So the term that goes under for the delta T measurements for the metal, T final, which is we don't know. I'm gonna measure it later on, which is coming up. And that number does not go down. Okay, very good. All right, so I guess stuck at that value, which is fine. So T final minus the T initial. What's the initial temperature of that hot metal inside the boiling water? It was 90.3. So I'm gonna write down 90.3. Equals on the other side, he's a negative. Now, every Q term, every heat measurement has the set of three terms: mass, specific heat, delta T. Now we're going to concern all these measurements with the water measurements. What's the mass of the water? So the first term for the water.
Or 74.5.
Right, so I'm going to write down 74.54 grams. Times the specific heat for the water. What do you think? What's that number? What's the specific heat value for the water?
4.184 joules.
Very good. So 4.184, and this is in joules per gram Celsius. So this is in joules per gram Celsius times delta T for the water. All right, which is typically the final temperature, which is coming up, minus the initial temperature. And what was the initial temperature for the water? I guess that is the measurement. Let's just get an idea of what's going on. So this is, yeah, so that temperature does not go down, so we can stop the process, okay, if you want. Okay, so you're gonna go back and just stop that process, which is fine. Okay, so the process did not go beyond that number. Okay, so it resists to go down. All right, so here's the cursor. Okay, at the initial temperature, and can you see those values? So can you look up that window, the X and Y, and locate that initial value of that temperature? So that initial temperature, can you see that Y value of the cursor? Can you look at
21.85?
Right. So 21.85. So I'm going to write down. So this is 21.85. So that was the initial temperature. The final temperature is coming up. Okay, so let's erase and try to analyze. Let me show you how to analyze the final temperature. Very simple. So first, so here's the plot. Let me just enlarge that plot. Let me just write down 28. Okay, so here's the plot. So first, I want to highlight the most linear portion of that plot. So which is that portion. Okay, that's the most linear. So avoid something that has kinks and kind of features that are artificial due to somehow touching of metal suddenly with that temperature probe or something that you've done. Either you should be mixture or you've done something. But then just locate the area which is like a smooth descending temperature. Okay, but it has to be the most linear portion of that plot. So I highlight that most linear portion of that plot. I want to create a straight line. Like here's a ruler, and I want to just draw a straight line. That's all my intention. So I'm going to create a straight line. Here's a nice equation for it. Who cares? All I've done basically is, here's my straight line. I just created a straight line. Okay. So from that straight line, I want to go to analyze and just interpolate. So I'm going to bring that cursor until the initial time mix in. So this is when I mix the metal with the water. See that little kink? When the temperature starts to spike, starts to jump, that's when I mix the metal with the water. Around that time, okay, can you read? So here's the window. So locate the temperature inside that window. So here's the beginning of the mixer, mixing the metal with the water. Can you read that temperature?